Hi scholars, Ms. Beglin here with your Unit 2 Molecules, Topic 3 Gases, Lesson 2 Gas Laws wrap-up. In this video, I'll be summarizing the results of our simulation and defining the different gas laws that you should be familiar with. So let's start with the relationship between pressure and temperature. As I said in class, every single group investigated this. So I pulled one group's data, summarization, and explanation. So here we can see that this group investigated the relationship between pressure and temperature by holding volume constant and increasing temperature from 10 degrees Kelvin to 500 degrees Kelvin, excuse me. And as they increased the temperature, the pressure also increased. They summarize this really well in their summary statement. As temperature increases, pressure increases. As temperature decreases, pressure decreases. And they explained it really well too. And I'm going to pair their explanation with this visual. As the temperature increases, the pressure increases because having a higher average kinetic energy means that the particles are going to collide more frequently. Excellent. The only thing that I would add is that they're also going to collide with more energy. So this is actually one of our gas laws. It's known as Gay-Lussac's law. At a constant volume, as pressure increases, temperature increases, and vice versa. So we see that as temperature is increasing, pressure is increasing. The cool thing about the gas laws is that you can represent them mathematically. So Gay-Lussac's law is represented mathematically as P1 T1 is equal to P2 over T2. And what this means is that if we take a gas under certain conditions of pressure and temperature and change one of them, either the pressure or the temperature, we can predict the remaining property. So you can think of T1 as, or you can think of the 1 as indicating the initial and the 2 is indicating the final. This is true for all units of pressure. Pressure is commonly measured in ATM, millimeters of mercury, torr, and kilopascals. The conversions between you can see below. Temperature must be in Kelvin. And as a reminder, to convert between Celsius and Kelvin, we add 273.15 to our temperature in Celsius. The reason for that being is these relationships are only linear when the temperature is in Kelvin. Now let's look at the relationship between pressure and volume. Two groups actually had some extra time, so they looked at the relationship between pressure and volume, which was awesome. So I've pulled one group's observations, summary, and explanation. As volume decreases, pressure increases. There is an indirect relationship. As they said, there is an indirect relationship between volume and pressure. Their explanation is spot on. Volume is a measure of space. The less space, the frequency of particles hitting each other is higher. Contrary, with more space, particles have more room and the possibility of hitting each other is lower. And again, that's what pressure is. It's a measure of the force of collisions. And I would pair that explanation with this visual. This is known as Boyle's law, which states that at a constant temperature, as pressure increases, volume decreases, and vice versa. Here we can see this represented graphically. And it's also represented mathematically. The nice thing about Boyle's law is that it works for all units of pressure and all units of volume. I showed you the units of pressure before. Volume is typically measured in liters, milliliters, or cubic centimeters, the conversions for which you can see below. Let's talk about volume and temperature. No group investigated this combination, so I'm going to jump to the gas law. At a constant pressure, as temperature increases, volume increases, and vice versa. For the explanation, we're going to use pressure as an intermediate. As temperature increases, pressure is going to increase. We know that. This is going to push the walls of the container out, and so our volume increases. The best example of this is actually if you leave a balloon out in the cold. As the temperature decreases, the balloon shrivels up because the gas particles are moving slower and slower, and they can't hit the balloon with enough force to keep it expanded. So it shrivels up. Here we can see a graphical representation of this relationship. As temperature increases, volume increases. As temperature decreases, volume decreases. Mathematically, this is represented as V1 over T1 is equal to V2 over T2. And this law is valid for all units of volume, but temperature must be in Kelvin. We can combine Boyle's law, Charles's law, and Gay-Lussac's law to produce the combined gas law, which relates the pressure, volume, and temperature in an initial condition to our pressure, volume, and temperature in a final condition. The rules for the units are the same. So this works for all units of pressure and volume, but temperature must be in Kelvin. The last gas law we'll be discussing is Avogadro's law. At a constant pressure and temperature, as the amount of a gas increases, the volume of the gas increases. And that kind of just makes sense, right? As we're blowing up a balloon, we're adding more and more gas particles to the balloon, and the balloon gets bigger and bigger. More stuff takes up more space. The really cool thing about Avogadro's law, in addition to helping us discover Avogadro's number and defining the mole, is that it revealed that the volume of 1 mole of a gas at standard temperature and pressure, so 0 degrees Celsius and 101 kPa or 1 atmosphere, is equal to 22.4 liters. This is true for any gas. And it is referred to as the molar volume of a gas. That's all, scholars.